Hi, my name is Amy Lee, an application engineer in the Precision System Business Unit at Texas Instruments. Today I'm going to show you how to do a ratiometric configuration of an RTD sensor. So the challenge here is what is a ratiometric configuration and how you can use it to increase the performance of your sensor signal path. So let's take a look. So an RTD sensor stands for resistance temperature detector, and this resistance changes linearly as temperature increases. So typically a part number for an RTD is PT100 or PT500. The last number of the part number represents the resistance at 0 degrees Celsius. So in this case, at 0 degrees Celsius, this RTD will have 100 ohm, and this resistance will increase as temperature increases. In this case, we have a 3-wire configuration, wire 1, wire 2, and wire 3. Now, the RTD will have a bias current. In this case, it will be IB1 and IB2, converting this resistance to a voltage. The voltage of the RTD will be connected to some sort of amplifier and or a digitizer, such as an ADC. In this example, we will use the LMP90100. It's a 24-bit sigma delta ADC with an amplifier, programmable amplifier with a gain of 1 to 128. And the RTD will be connected in a ratiometric configuration where the bias current will also be sourcing this external resistor for your reference, and this reference RF will be sourcing the VREF for your ADC. So let's see how this ratiometric configuration can also reduce your sensor signal path. Let's take a look at the equations on the right-hand side. Let's first write the equation for VREF. VREF is just IB1 plus IB2 times RF. So let's take a look at the diagram to see how that works. Here's RF, here's VREF setting the voltage reference for your ADC. And as you can see, IB1 and IB2, the bias current, is flowing through this external resistor, setting the voltage reference. Now let's take a look at how you can write the equations for the channel that the ADC will sample. In this case, the channel will be Vn0 minus Vn1. So going back to the equations, Vn0 is just the IB1 times the line resistance plus the RTD plus both of the bias current times the third line resistance plus the external RF. And you can also use the nodal equations to write your equations for Vn1. And the channel that the ADC will sample is the difference, Vn0 minus Vn1. And if you write down all the equations, essentially you will eliminate all the line resistances and the bias current to get the Vn of IB1 times RTD. So at the output code of the ADC is Vn times the gain times 2 to the 24 because it's a 24-bit ADC, times 2 divided by 2 times VREF. And if you plug in your equations for Vn as IB1 times RTD and your VREF as IB1 plus IB2 times RF, what you can see here is that you can cancel IB1 and IB2 because they're essentially the same, and your output ADC code, your final equation, will eliminate IB1 and IB2. So what you have is RTD times the gain times 2 to the 24 divided by 2 times RF. And you can see that with this ratiometric configuration, you've eliminated any reference error contributed by the bias current IB1 and IB2. So that's how a ratiometric configuration works. So in summary, in this video, I've shown you how to do a ratiometric configuration for an RTD sensor. With a ratiometric configuration, you will eliminate the bias current error of your ADC, therefore increasing the performance of your sensor signal path and of the ADC itself. If you have any further questions regarding what we talked about here today, particularly the LMP90100, go to the following web addresses. Thank you for watching.